Okay, good evening. Sorry for being late. So last time we talked about kinematics, robot kinematics. Today we will talk about robot dynamics. And later on we'll get to the control. Maybe some we'll talk about some statics and some constraints, and then dynamics, and then control. So now we are going to, we talked about kinematics and the transformation matrices, and now we will talk about the Jacobian. So say we have a robotic arm, as you can see here, but not only a robotic arm. And we can say the forward kinematics is in terms of the configuration parameters of the arm, which are Q. Q are the configuration parameters, and F is a function of the configuration parameters, say the angles of the joints, and that map the configuration parameters into the location and orientation. Say now for the location of the end of the arm, the end of the tool, as you can see here in the picture. So this is the forward kinematics is x is x. What it's, no, I can't see. Yeah. So x is the position and orientation of the end of the arm. F is the function, the forward kinematic function, and Q are the parameters of the joints, of the configuration parameters, say the angles of the joints or linear distance of linear joint. Then if we want to know the velocities, then we can take the derivative, the time derivative of the forward kinematics. And when we take the derivative of the forward kinematics, the derivative of F, df to the q times q dot, we get x dot, and x dot is the position, the velocity of the end effector. Df to the q is the Jacobian matrix of the robot, and J, the Jacobian, is a matrix that depends on Q. Let's do an example. If we have a robotic arm with two links, as you can see here, theta 1, theta 2, then the forward kinematics, as you can see, x and y. X is L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Y is the same with the sine. And the orientation of the end effector is simply theta, which is theta 1 plus theta 2. This is the forward kinematics we saw last time, how we can do this. How we can compute this using the homogeneous transformation matrix. Now, if we want to take the Jacobian and actually compute the velocity, then we take the derivative of these equations. So if we take the derivative, J is the derivative, as you can see here. J is the derivative of f. This is f1, 2, and 3. df to the theta 1 and theta 2. And also we have the angular Jacobian here, which is taking the derivative of the last function, the orientation, with respect to theta 1 and theta 2. So we have the linear Jacobian and the angular Jacobian. And we simply took the derivative of x and y. You can see x dot is the derivative of this L1 cosine theta 1. The derivative is minus L1 sine theta 1 times theta 1 dot. And the derivative of this is L2 cosine theta 1 plus theta 2 is minus L2 sine theta 1 plus theta 2. This is derivative with respect to theta 1. So we multiply it by theta 1. The next column is the derivative with respect to theta 2. Therefore, we have here just the derivative of the second part, which depends on theta 2 minus L2 sine theta 1 plus theta 2 times theta dot 2, as you can see here. This is how we do this. Any questions about this? Oh, everyone knows this? Okay. Now, if we take closed kinematics chain, so we have a mechanism which is closed, not an arm, but something more complicated, like the 4-bar linkage, as you can see here, or anything else. Then we can no longer write the forward kinematics as a function of the configuration parameters. We have the input variables Q in, the output variables Q out, and we have the constraint equation now, which is f of Q in and Q out equals 0. So it's a little different because we cannot write the Q out as a function of Q in. And we need to do something else. So now we can take the derivative of f, which is a function of Q in and Q out, by taking df dq in times dq in to dt. This is the input Jacobian times the velocity of the input variables, plus df to dq out times dq out to dt. J out is the output Jacobian times the output variables velocity. And this is simply the derivative of the constraint equation. Therefore, when we took the derivative of the left part, then we took the derivative of the right part, which is 0. And we can get the relation between J out Q out dot to minus J in Q out Q in dot. Then we can talk about singularities. Singularity is when the Jacobian is not of full rank. So it's when its rank is less than a full rank. How we check if this happens? We simply take the determinant of the Jacobian matrix, and see if it is 0. If the Jacobian is not square, we simply take the square part of the Jacobian, say Jacobian times Jacobian transform. This should be the smaller part of the Jacobian. If the Jacobian says 3 by 6, then we multiply 3 by 6 by 6 by 3, and JJ transpose will be 3 by 3. And then for robotic arm, say F is the forward kinematics. It maps from Q the configuration parameters or the angles of the joints, to X the position of the end effector. Sometimes we call Q in and X the Q out, the output parameters. Then the Jacobian maps from Q dot in, actually the tangent space to Q in. This is T Q in, this is the tangent space to Q in, because this is from Q dot to Q dot out, on the tangent space to Q out. And in singular configuration, and the Jacobian simply maps from Q dot to 0. No output velocity. So there is some velocities that we cannot provide. And you see that in singularity, joint velocities are mapped to 0 velocity at the end of the robot. But the system is not necessarily stuck. It simply cannot provide velocity in certain direction. Any questions about this? Did you learn this before? No? If we say my arm is like a robotic arm, if it's fully stretched, I cannot provide velocity in the direction in and out. Like this, I cannot provide anymore, because any movement will move it up, down, or sideways. My arm actually is not in singularity because I have redundancy. Another term that you should understand is the constraints, and we'll talk a little bit about constraints. When there is a constraint in the form of a relation between the configuration parameters, the constraint simply reduces the number of degrees of freedom. So say, for example, I have two particles. Each of them has 3 degrees of freedom. So together they have 6 degrees of freedom. Each of them can move freely, but I connect them with a rod in a length of L. And therefore, I have a constraint now that the distance between these two particles is L. Therefore, instead of 6 degrees of freedom that I had when I had two particles, now I have only 5 degrees of freedom. You see, 3 degrees of freedom times 2 particles minus 1 constraint. You can also think about it as I have the position of 1 particle, which is 3 degrees of freedom, and 2 angles between the 2 particles. Because only 2 angles, this and this, this elevation and azimuth, those two angles say actually what will be the position of the determine the position of the second particle. Therefore, we have only 5 degrees of freedom, and we can represent this is x, y, and z of particle 1 and theta and phi of the relative angles of the rods. So, if I have a particle with a configuration XYZ, and it is subjected to a constraint of the form f of xyz equals 0. So this can be any time or any type of constraint. We can look at this as a particle in the space xyz, but it is constrained to move on a manifold f. The manifold is that f of xyz equals 0. This is type of the geometry of the of this. And therefore, the constraint reduces the 3 degrees of freedom into 2 degrees of freedom, 2 parameters of the manifolds. It's a 2-dimensional manifold in a 3-dimensional state. We ask that the constraint will be twice differentiable. We said that F is a 2-dimensional manifold in a 3-dimensional space. And the velocity of the particle, since the particle has to move on the manifold, therefore its velocity is tangent to the manifold, because it cannot leave the manifold because of the constraint. So the particle's velocity is tangent to the manifold. If we take the time derivative of the constraint, we get here this equation, df to dx time x dot, and so on. This is the derivative of the constraint. And we can see that this is simply the gradient of df with respect to x times the velocity x dot y dot z dot. Let's talk about the gradient. If I have a function f of x and y, and I draw the function x and y and f, then df to dxy is tangent to the manifold f of x and y. You see the f of x and y. This is the graph of the function. But if I take a level set of the function and say f of x and y equals 0, this is kind of a level set of this function in an x and y space, then the derivative df to dx and y is perpendicular to this manifold, this constraint manifold. Actually, fxy equals 0 is a constraint manifold. It's a level set of this, and when I draw and look at it from above, I get something that is perpendicular to the level set. So, when I look at the constraint, I again go back to the example that I did before. So I have a 3D space, x, y, z, and I have a constraint f of x and y and z equals 0. So the particle has to move on this constraint. When I look at the normal to the constraint, normal to this manifold, is simply df dx, df dy, df dz. This is the vector n, which is perpendicular to the manifold. When I look at the velocity of the particle, which is x dot y dot z dot, this is the velocity of the particle, and this must be tangent to the constraint manifold. Therefore, since the normal is perpendicular to the tangent velocity, therefore the dot between the normal and the velocity is 0. This also comes from the math, but also from the geometry, because they are perpendicular. Is this understood? Now we can talk about Pfaffian constraint. Constraints can be in different types, but there is one unique type of constraints called Pfaffian constraint. Pfaffian constraint is in the form of something multiplied by the velocity. Like here, df dx, df dy, df dz multiplied by x dot y dot z dot. This is type of Pfaffian constraint. And we can have a constraint that reduces the number of degrees of freedom. This is called a holonomic constraint. We can have a constraint on the velocities. This is a non-holonomic constraint. And we have something in between, which is a constraint on the velocity, but in a specific term called a Pfaffian constraint. And we can also take this as infinitesimal displacement in dt, and this is dx, dy, dz. That's the type of constraint that is called Pfaffian constraint. And when we have a constraint, we not only have the constraint that the particle here or the dynamical system has to follow, there is something that has to cause the dynamical system to follow this constraint. And this is the constraint force. Otherwise, if there will not be force, the constraint won't be remained. It will be broken. So there must be a force that will constrain the particle to move on the manifold. The constraint force is normal to the manifold, because if the particle wants to leave the manifold, there must be a force perpendicular to the manifold that pushes it back into the manifold. So we can write this force as some coefficient alpha times the normal to the manifold. And this is f hat. And from that, we can say that each element here must be true. So from we have the dn. dn is simply, as you can see here, dn is df dx, df dy, df dz. And if I multiply them by alpha, I get f tag. And there is f tag x equals alpha times df dx. And therefore alpha is equals to f tag x divided by df dx. That's what we have here. And therefore we can do this the same. This is also alpha, and this is also alpha. And therefore they are the same. And we can define infinitesimal displacement of the particle. So the particle here can have a small displacement, dx, dy, dz. We call this dr. So it moved a little bit to any direction, infinitesimal movement. And then we can say that we have the f tag, the force, equals alpha dot n. We have the displacement of the particle dx, dy, dz. Then the work that this force does when the particle moves along a distance, a work is a force times the displacement, right? Then the work, the infinitesimal work that it does, this particle does when it moves along dr is simply f dot dr. And f dot dr, f dot is alpha dot n times dr is this. But we recall that here df dx, or better, it was, where is it? It was here. df dx dx, df dy dy, df dz dz equals 0 because of the constraint. Therefore, we get the work that the force, the constraint force does when it moves the particle along dr, and dr must obey the constraint, must be on the manifold. Therefore, this force times dr is alpha n dot dr dx dy dz, and it is 0, as we said before. So the work of the constraint force is 0. So there is no energy that comes out of nothing. We cannot generate energy. This means that the work that of the constraints is 0. That's the idea of the constraint force. Now we learn about the principle of virtual work. So say we have virtual displacement, which is the displacement of the generalized coordinate that respect the constraint. So we have a particle that has some trajectory, and we virtually think about a displacement of this particle. So we take the particle from its position and move it virtually by our thinking in a dr direction, but it must obey the constraints, this virtual displacement. So the displacement dr is delta x, delta y, delta z. Small displacement of the particle. Since the displacement meets the constraints, therefore F is the constraint, as you recall, the constraint equation. So df dx, df dy, df dz times delta x, delta y, delta z. And that must be zero because of the constraint. Therefore, when we talk about the work, the virtual work that is done along a virtual displacement that meets the constraints is f tag dot delta r. Delta r is the virtual displacement, and this must be zero. And this is a very useful equation, very useful rule, the rule of virtual displacement, of which virtual work. And we'll later on see how we can use this to actually compute forces and torques in a mechanism. But before that, let's go back to define the Pfaffian constraint. So a constraint of the form, I'll start from the end, of the form of a matrix A times Q dot equals zero. This is called the Pfaffian constraint. So let's start from the beginning. If we have a constraint A, say y, A, Z times dx, dy, dz, the virtual displacement that meets the constraints is, instead of dx, is delta x, delta y, delta z. And the constraint force is some force lambda that is perpendicular to the displacement. So it is ax and y, az, ax and y, az. And therefore, we can write that the general form of Pfaffian constraint is the A matrix times Q, which is the displacement, Q dot, which is the displacement, dx, dy, dz. And this must be zero because of the principle that a constraint does not generate energy, does not has energy from its own. And let's see here an example. If I have a particle, which is its coordinate is x and y, and it has it is connected by a wire, by a string in a length of L. Therefore, the constraint now is L dot V. V is x dot y, and it must be tangential to the arc that the particle is doing, is moving along. And the constraint here is x and y because we have actually this is the constraint equation. X squared plus y squared equals L. And we can take the derivative of this, which is 2x plus 2y. So this is x and y here. the 2, it doesn't matter because of the 0. And this is x dot plus y dot. And this is actually the constraint. X dot plus y dot is x dx dt plus y dy dt. If we multiply each side by dt, we get x dx plus y dy. This is the constraint equation. And if we take the integration, we integrate this, and this is the constraint equation. We integrate this integral of x dx plus y dy. This is x squared plus y squared plus c. And the c is the constant of the integration. And conventionally, we can write the constraint x squared plus y squared equals L squared. And this is the type of constraint you see that we can get from here to here or back. And so it is a matrix time the x dot and x1, which is again similar to the Pfaffian constraint. Any questions?
Pfaffian constraints supplies a condition to calculate
Pfaffian constraint is simply a constraint.
yes.
Constraint on the velocity.
Because as a condition to use our configuration on kinematics, use these constraints
To do what?
to get some to get the constraints of the coordinates of the kinetic.
So actually here, this is not a Pfaffian constraint. This is a constraint on the coordinate, on the configuration. But we transform this to a Pfaffian constraint by simply taking the derivative or taking the integral of this and get this. Pfaffian constraint is convenient because we can then find a way how to calculate the dynamics even if we have Pfaffian constraint. If we have a non-holonomic constraint, solving the dynamics is harder. And solving for the constraint forces are harder.
Is there any physical meaning of Pfaffian constraints? Intuition,
yes.
For example.
So this is the intuitive example. And so it can, but in general, it's a type of constraint that we can deal with. It's not a non-holonomic constraint, which is very difficult because it constrains the velocity to be able to move or not to be able to generate velocity in certain directions. Say our car, we cannot park our car sideways. So I have, if I want to park my car, I have to do some kind of a maneuver in order to get sideways. This is a non-holonomic constraint because the constraint is that the velocity has to be along the wheels. This Pfaffian constraint is still a constraint on the velocity, but is much easier to work with than the non-holonomic constraint. So now we are getting to holonomic and non-holonomic constraint. Say, if we have a constraint in the form of a function of the configuration equals 0, then we can have many of them. This is called a holonomic constraint because this is constraint on the configuration, not the velocity. But we can take a holonomic constraint, and this constraint simply reduces the number of degrees of freedom. Say, as before, I had here. I had two particles which had 6 degrees of freedom, and now I connected them with a rod, and therefore now I have 5 degrees of freedom. That's the meaning of a holonomic constraint. There is a constraint. This is the constraint equation. It's equation in terms of the configuration variables x1, x2, y1, y2, z1, z2. So I have a constraint on the configuration variable, and now I can reduce the number of variables, numbers of configuration variables, like this, like the 5 here. And this is the meaning of holonomic constraint. But each holonomic constraint I can transform into a Pfaffian constraint. How do I do that? I simply take the derivative. So if I take the derivative of the holonomic constraint, dh to dq times q dot, because this is equals 0, 0, so the derivative of this is also 0. Therefore, dh dq times q dot is 0. And this is actually a Pfaffian constraint. This. So it's a matrix. You see this matrix times the velocities, q dots, and this is the structure of the Pfaffian constraint. So I can handle any holonomic constraint as a Pfaffian constraint. And later on we'll see what we can do with that. Let's have a break, and then we'll continue. So we continue. So we had the holonomic constraint that is a constraint on the configuration, and by taking the derivative of this constraint, we can write it as a Pfaffian constraint. Now, if we take the constraint forces, we can mark them as capital gamma, and they are in the direction of the normal to the constraint manifold. Therefore, the constraint manifold, the normal to the constraint manifold is dh times dq. And lambda is simply the amplitude, the amount of force. So this is the amount of force, this is the direction of the force, and the work of the constraint force is the constraint force times the velocity. And we already saw that this is the energy and it must be 0. And therefore we can write this as lambda gamma dot q if we take two vectors with the dot product, A and B, say, we can write them as A transpose times B, which for vectors. So lambda dot times q dot is simply lambda transpose times q dot. Transpose is taking the transpose of this, taking the transpose of multiplication is taking the opposite and transpose of both. So it's lambda transpose times dH dq transpose, but dH dq is a symmetric matrix, and therefore the transpose is the same because it's a matrix of it's a Jacobian matrix. It's a matrix of the derivatives, and therefore it must be symmetric. And dH dq is simply dH dq transpose is simply dH dq times q dot, and this equals 0. If we have a Pfaffian constraint of the form of A times q dot, A is some matrix times q dot, then for a constraint of the form of h of q equals 0, A will be dH dq. So A of q is simply dH dq. And therefore, we can write this as lambda transpose A q dot equals 0. And that's it. Pfaffian constraint of the form can be holonomic if there exists H, something like that. And if there is H, we can integrate it as we saw before, and then reduce the numbers of degrees of freedom. Otherwise, it will be a non-holonomic constraint, a constraint on the velocities. So a non-holonomic constraint is a constraint on the velocity. A velocity constraint is said to be non-holonomic if it is of the form of a function of q and q dot equals 0. This is in general a non-holonomic constraint. It cannot be integrated, and therefore we cannot reduce the number of degrees of freedom or the number of configuration parameters. An example of a non-holonomic constraint is simply a wheel rolling on the ground. As you can see here, we have a wheel that is rolling. So we have a phi angle for rolling, we have a radius, and we have a theta angle for the steering direction. As you can see here, we have x and y, and we have the direction of rolling, which is theta, the direction of rolling, and we have phi, which is the angle of the wheel. And the system has only, it seems that the system has only 2 degrees of freedom, theta and phi. But we have, we can't find a relation between x and y and theta and phi, because we have the relation between dx dy to r d phi cosinus theta. So r d phi is how much it advances, and it advances, the wheel advances, it advances in the direction of theta. So here we have cosine, here sine, and we have dx dy. And this is in general the kinematics of the wheel rolling on the ground. But we cannot find the relation between x and y and theta and phi. And the problem is that we can get to the same xy position with different orientations. So I can get in a direction like this and that, and also move forward here. But here I got in this orientation, and when I get here, I got in 90 degrees orientation, which is different So I've got same x and y, but different theta and phi. So there is no one-to-one mapping between x, y, and theta and phi. And that's the problem of non-holonomic constraint. We cannot change coordinates very easily. And the direction is important. And I told you another example of the car that needs to park. We cannot supply velocity in any direction. Also, the wheel cannot provide velocity in a sideward direction. It needs to turn and then move. So that was a chapter on constraints. We'll use it later on when we'll talk about dynamical systems with constraints and how we solve them. But currently, just keep this in mind. We'll move to different but related subject, which is the principle of virtual work. It is related because we talked about work of constraints. So here we take the virtual work, the work along virtual displacement that happens in our head and not in the real world. That's the meaning of virtual. So let's begin. Let us assume that there is a system with n particles. The force which is applied on each particle is Ri. With the index I. This is the force that is applied on each particle. For each particle to be in equilibrium, we need that the sum of forces on the particle will be 0, right? In equilibrium. Therefore, if we move each of the particle a little bit by a virtual displacement that we think of, we just move it a little bit, delta R, and we know, or we want the particle to be in equilibrium, then the work that is being done by this small displacement, because we have R, which is the force acting on a particle with a small displacement, this work has to be 0 in order for the particle to be in an equilibrium, in order not to move. That's the meaning of equilibrium. Therefore, the total sum of work that was done on all the particles is simply the sum of the force multiplied by the virtual displacement. And in order for the whole system to be in equilibrium, this must be also 0. Because each one of them has to be in equilibrium. So if there is, in addition to the work between that external work that acts on the particles, there's also internal constraint work, constraint force that is act on a particle. Therefore, I can rewrite the total force on each particle as the force, the external force that is act on the particle, in addition to the constraint force that holds the particle to, say, a manifold, to a certain constraint. And therefore, the total amount of work that is done by the forces, the external force, and the the constraint forces will be this sum F dot delta R plus F tag, which is the constraint force dot delta R. But this, the constraint force, we already saw that this is zero, because constraint force, the work of constraint force is zero. And therefore we left with only the external forces. And the work of the external forces times small displacements of the system parameters must be zero in order for the system to be in an equilibrium. Therefore, we get the principle of virtual work. So we have n particles. On each particle, we have an external force. It doesn't matter if there is constraints, if there are constraints. If there are constraint forces, that doesn't matter. We have the external force times the virtual displacement, small displacement. And this must be zero. This is the work of all external forces along virtual displacements. Small displacement in our head is zero. And now we can apply this to a robot. For an equilibrium of robot. Okay. So we have a robotic arm. It has several joints. And at each joint, there is a motor that applies a force or a torque. If it's a linear joint, it applies a force along the joint. If it's an angular joint like this, it applies a torque in the joint. This set of forces and torques, we call it tau. Actually, we talk now just on one joint. So there is one torque in each joint, in the motor of each joint. Okay? And each joint has an angle Q. So we can think of a small displacement of this configuration, Q, as a delta Q. Also, on the end effector, at the end here, we have a tool. The tool applies force on the environment. So we can think of this as the environment applying force on the robot. Say I want to screw something, so there is a torque and there is a push force. And the screw also applies on the robot force and torque. This is the F and T of the end effector. The end effector applies, so the environment applies a force on the robot, on the end effector. And this force is applied along a virtual displacement, along the movement of the end effector. Movement of the tip of the screwdriver. The screwdriver has a position x is x, y, z, and an orientation theta, which is theta 1, 2, 3, something like this, 3 degrees of freedom, 6 degrees actually. Theta meaning the orientation, 3 parameters for the orientation. So now I can think of the total work that is done on this robot. So we have tau, which is the torque in the joints. We have delta Q, which is small displacement, virtual displacement of the joints. plus the force and torque on the end effector times small displacement of the end effector, delta x, delta theta, of the end effector. In order for the whole system to be in an equilibrium, so the forces will kind of sum up to zero, forces, torques, and the system won't move, we need all of this to be zero. This is the condition of the principle of virtual work. This is the condition for the system to be in an equilibrium. But now I can rewrite this dot product here and here as a transpose of two vectors. As you recall, A dot B is like A transpose times B. So this is simply tau dot delta Q is simply tau transpose times delta Q. And FP dot delta X delta theta is simply taking the transpose. So it's a row vector and not a column vector. FT transpose times delta X delta theta. But what is delta X delta theta? Delta X delta theta is small displacement of the end effector. The relation between delta X delta theta and delta Q, as we recall from, it's here. Delta X delta theta, as we recall from the Jacobian, is the Jacobian times delta Q. It's like X dot theta dot times Jacobian times equals Jacobian times Q dot. But if we take this X dot, theta dot, and Q dot for a small delta t, it's like delta X, delta theta, and delta Q. So this is the relation. And we can substitute this here and get delta X delta theta equals J delta Q. This is everyone understand this? Okay. So now we can take delta Q outside. And we can write tau transpose plus F transpose T transpose times J. All of this in parentheses times delta Q equals 0. But this must be true for all delta Q, for every delta Q. And therefore, what is in the parentheses must be Q, must be true, must be 0. So this must be true equals 0. This must be true for all delta Q. And therefore, what is inside the parentheses must be also 0. And therefore, we take the thing that is inside the parentheses, which is tau transpose plus Ft transpose times J equals 0. We can move this to the right, the Ft with J, move this to the right with a minus sign, to the right side. Then take the transpose of both sides. If we take the transpose of this, we simply change the order and have transpose of both. And therefore, we get tau equals minus J transpose F. And this is the equation, the static equation of a manipulator, of a robotic arm. The tau, the torque in the motors must be equal to the minus external force times the Jacobian transpose. And this, when I have an external force, I multiply it by the Jacobian transpose, and that torque in each motor has to be minus this in order for the system to be in an equilibrium. Okay. Questions? Let's have an example. We have again a simple robotics arm with two links. Each link is L1 and L2. We have 2 degrees of freedom, θ1, θ2, and we have an external force at the end effector, F. The position of the end effector, as we saw before, F1, X is L1 cosine 1 cosine θ1 plus L2 cosine θ1 plus θ2. And again with the sine. We can take the derivative of this and have the Jacobian, actually the derivative of this function with respect to θ1, this is the first column, and with respect to the θ2 in the second column. And therefore we have the velocity of the end effector, and we have here the velocity of each joint, θ1 and θ2 dot. So this is the Jacobian, we saw this before. Now we can look at this Jacobian method and see when it is in singular configuration. We take the determinant of the Jacobian, this. And if we take the determinant of this, you'll see minus L1 S1 times L2 cosine 1, 2 times this, and this minus this times this. So this and this term just cancel each other, and we're left only with L1, L2 cosine sine 1, cosine 1, 2, and L1, L2 cosine 1, sine 1, 2, and together it's simply L1, L2 sine θ2. You can check this. And this is 0 when sine 2 is 0. When sine 2 is 0. When θ2 is either 0 or 180 degrees or pi. So it is either this configuration or the configuration when it's for back. And that means that the Jacobian has a reduced rank, and therefore we cannot apply a velocity in this direction. We can apply velocity only in this direction. Generate a velocity. Okay. Now we can talk about the statics. We know in equilibrium from the principle of virtual work that the torque in the joint equals to the minus Jacobian transpose times the external force on the end effector. Therefore, tau will be the minus Jacobian transpose. So we rewrite the Jacobian transpose. Actually, we took the transpose of this. This is the Jacobian. So we transpose this. First row will be first column. The second row will be second column. So we took the Jacobian transport times Fx Fy, the force that is applied on the robot by the impulse. It can be gravity, it can be external force due to some work that the robot is doing. So in singular configuration, when theta 2 is 0 or 180 degrees, this Jacobian is reduced to this because theta 2 is 0. So it's reduced to this. This means that that if we substitute Fx and Fy, a force in the direction of the robot, lambda cosine 1 sine 1, so it is in the direction of the robot. So if we apply this and substitute this direction, lambda is just the amount of the force, cosine 1 sine 1 is the the direction, so it's actually this direction, that, but this direction. But lambda can be negative, so it doesn't matter. Then what we get, if we put it instead of substitute instead of Fx Fy, you can see that we get L1 L2 S1 sine theta 1 times cosine theta 1, and we get this and this L1 L2 cosine theta 1 times sinus sine theta 1, and this cancels out. Now also here we have S1 times cosine 1, C1 times S1, so those also cancel, and we get total that this tau is 0. So it means that if I apply a force in this direction, I can have a 0 torque at the joint and still it will hold. That's the meaning of singular configuration. I do not have to apply torque in order to hold an external force. That's the idea. So we finish this and I'll get to the next presentation. Just a second. Yeah. I'll get to the next presentation. By the way, I uploaded all the presentations until the end of the course to the Moodle, so you can look at it. Okay. There was no video on the recording till now. I didn't see this. Yeah. Okay. So now we can talk about the dynamics, not only the statics, but we can get to the dynamics of the system. And we define a new quantity called Hamiltonian. Hamiltonian is actually the sum of the energy, the kinetic energy and the work of the external force. So it's T kinetic energy plus external force. But there are another type of forces called conservative forces. And conservative forces comes from potential energy. You can think about this as gravity. I can have a potential energy from gravity, but it can be spring, can be anything else that comes from potential energy. And then the force F that this kind of potential energy applies on the system is simply the minus of the gradient of this energy. So if for gravity it is mgh, right? The energy, the potential energy, then the force will be the gradient. Gradient h is the distance, then the gradient with respect to h is mg, and it's minus because it's down. And the potential energy is mgh upward. And it's again the same thing for spring. So for the potential energy for a spring is half kx squared, and the force is simply the derivative of this energy with respect to x, which is kx minus kx because it's back. And the work is the integral of the force along the displacement f dq. Okay. What? And if we substitute instead of f the minus of the gradient of the potential energy, we get minus gradient v dq, which is integral of gradient is simply v. So the work is minus v. And therefore, this is the work of the external forces, the external conservative forces on the system. And now the Hamiltonian, that was the total energy, as you recall, T plus W. But W is the work of the external energy, external forces. Now the work of the external forces is minus V. And therefore we can define the Lagrangian as T plus W, which is minus V. That's where the Lagrangian came from and why they defined it as a T minus V and not T plus V, as we may think of. Okay. The next subject is to actually take from the Lagrangian, develop the Lagrangian equation for finding the equations of motions, the dynamics of the system. So I want to develop the Lagrange equations, and this will be the next subject. And I think we'll take the break now because it's kind of a long story. Okay, so we'll do that. We'll take a break now for 10 minutes, and then we will continue with the development of Lagrange equations. Okay, so we will continue. So we go to the Lagrangian, which is the sum of the kinetic energy minus the potential energy. And now we get to the principle of least action, which is kind of the principle that governs the nature. That nature wants to have the minimum amount of action, and we'll define what it is action. Action is the integral of the Lagrangian between two times. And the principle of least action said that if I take some kind of a deviation from this, then it has to be zero. The derivative, something like the derivative of the action has to be zero, or the change. So along motion trajectory, the action is minimal. So every variation from this trajectory will increase the action, and therefore the delta of this action, it has to be zero along the trajectory. So if we have here L of x1 and x2, x1 and x2, x is the configuration of the system, and the system is moving from T1x1 to T2x2 along some trajectory. Then I can deviate a little bit, some variation of the path, the trajectory of this, and the action, the system will find the path, the trajectory, such that the action, this action will be minimal. So let's see how this works. The action in the sections A and B is simply the integral of the L of the Lagrangian along this. So this is the LA, the Lagrangian along the A section times delta T plus the Lagrangian in the B section times delta T. To find the minimal action, we take the time derivative of this and equals this to zero. So taking the time derivative of S along sections A and B, dSAB, taking this derivative with respect to x and x dot, because L is a function of the configuration parameters and their velocity, x and x dot. So if we take this in two sections, A and B, we have LA dt plus LB dt, so it's dLA dx in section A times dxa dx delta t. but I need this also in x dot. X dot is VA, the velocity along section A. So it's dLA, dVA, dVA, dx, delta t. This entire thing is the derivative of LA dt. And we do the same for LB, delta t. So it's a bit long. And this must be 0. Now, if we set x to be somewhere in the middle, then xa is in the middle of section A. It's x plus x1 divided by 2. The velocity in section A is simply the velocity of getting to from x1 to x along delta t. So it's x minus x1 divided by delta t. Now we can take dxa to dx. Dxa to dx is simply x over 2 is half here. dva to dx is x over delta t, so it's 1 over delta t. This is in section A. We do the same in section B. And then we can substitute everything into the previous equation here, and get this equation. dsab to dx x dot. That this was the long equation. We substitute all of these relations with x, a, and b, and all of this, and got these things. 1 over dLA dxa plus dLB dxb. What is dLA plus dLB dxa dxb? It's simply dl to dx. And minus 1 over delta t, dl dv, dl dv, dl dv is simply dl dv over the delta t is dl dt, d to dt of dl dv. All of this multiplied by delta t, but this has to hold true for all delta t. Therefore, the things that here in the parentheses has to be 0. And what we get is simply dl to dx plus minus d to dt of dl to dv equals 0. And yeah. And what else? Then the numerical derivative is x minus f times delta t divided by delta t, and therefore we get d to dt of dl to dv. And everything is in minus. And we got the Lagrange equations of motion, dl to dx minus d dt, dl dv equals 0. And this is something that you probably know. So if we have the Lagrangian, which is a function of q1 and q2 until qn, and q dot 1 to q dot n, the Lagrange equations of motion is simply d to dt times of dl to dq dot k minus dl to dqk. And this should be 0. And it should be for all the configurations parameters K. This is clear? You all know this? Okay, good. Now we can discuss external forces. When there is an external force, that cannot be expressed as a derivative of a potential function, of a potential energy. So the work of external forces is simply the force times the displacement, delta R, where Rj is the point where the force Fj is applied, is act. The displacement delta R can be expressed, delta R, as the sum of dr dot delta times delta k. dr to dk delta k, delta qk. So the work of the external forces is the sum of all the forces of Fj dot the delta Rj, which is the sum of dr to dk times delta k. Now that we have the energy of the external force, the work of the external force, actually here, we can change the order of the sum here. So it can be for each configuration, each delta, there will be the sum of all the forces times drj dqk. drj dqk is the derivative of the point where the force is acting with respect to the configuration parameters. So we can take all of this inside here and say, this is the generalized force. This is what the mechanism feels as the external force when we have a force applied on the end effector. This is what each joint will feel, because this acts along each delta Q. So we have the Fj dot delta Rj. Now we get back to the least action principle, but we add here the action of the external force. So this is the least action, the regular least action, or the action actually. This is the action, and this is the action of the external force. We have here the generalized force here, and yeah, Qk times delta Qk is the work of each force of all the forces. This is all the forces along one coordinate dt. So if we take the delta Q outside, delta Q delta dt, we take this outside, we get here the Lagrange equations, and here the generalized force. And this must be 0. And now we get the Lagrange equations of motion with external forces. So the external forces here, since everything has to be zero, so here we got minus qk. We move this to the other side, so it's plus on right hand side, and we get the Lagrange equation of motion, where we define the generalized force as the sum of the external force dot the derivative of the point where the point where the force is acting, and the dr to dq is simply the Jacobian. And since we have dot, we can change this as F transpose dr dq, or take the transpose of this in order to be a column vector, and it will be J transpose X. And we take only the J element of this matrix, of this vector. So to conclude, Lagrange equation of motion, the Lagrangian is the kinetic energy minus the potential energy. The kinetic energy is a function of Q and Q dot. And the potential energy is a function only of Q, like mgh, like kx, k squared. So it's a function only of Q. Therefore, we can write the Lagrange equation of motion, where we substitute T of Q dot and V of Q. And therefore, where we have dV le dq dot, it simply vanished because there is no q dot. So we get dt to dq dot, not dv to dq dot. ddt, dt, dq dot. But now we have also t and v, which are function of q. So we have this t minus v, but we have minus, so it's minus dt dq. Minus, it's plus dv dt. And this equals to the generalized force. So this is the idea. Now we can get to be specific, how we compute this. Okay. So if I have a system of particles, each particle has a mass m, mi, and a velocity vi. So each of one of them has a kinetic energy of half mv squared, right? But it's not mv squared because v is a vector. So instead of v squared, I write v transpose v. So half mv squared, this is the kinetic energy. But if I have a rigid body that can also turn, not only move, so it has a kinetic energy of the movement of the center of mass. Vc is the velocity of the center of mass, and also the rotation velocity. This is the omega here is the angular velocity. So angular velocity transpose times the inertial matrix, three-dimensional, 3x3 inertial matrix of a rigid body. So omega transpose I omega, half of it, is the is the inertial, is the kinetic energy of rotation. But keep in mind that I has to be in the around the center of mass, because we took VC. So I has to be also rotation around center of mass, and it has an omega has to be in the same coordinate system where I is computed. If this is in the joint coordinate system, also omega has to be in the same coordinate system. Coordinate frame, actually. So Vc is the center of mass velocity, omega is the angular velocity of the rigid body, and I is the inertial matrix around the center of mass. And all should be in the same coordinate frame. So I is the inertial matrix around the center of mass. So I is a matrix, Ix, Ixy, Ixz, and so on, where Ix is the integral of y squared plus z squared dm, and so on, as you see here. You probably learned this in dynamics. Yes, note that omega and I must be expressed in the same reference frame. So let's take a very simple example. If I take this card that is connected with a spring to the left side, and it has configuration parameter x as the displacement along the x. And there is an external force F that is applied on this card. So if we take Newton law, F equals ma, so we have ma, mass times the acceleration, and the total force is simply F minus k, x minus x0. X0 is the free space of the spring. That's it. That was very easy. Now let's try to do that, but not in Newton, but also according to Lagrange. So the kinetic energy is half mx dot squared. The kinetic energy of this, because the velocity is x dot. The potential energy of the spring is half k x squared, but x is not x, is actually x minus x naught. X0 is the amount of the displacement of the spring. So the Lagrangian is T minus V, and it's this expression. So we take this expression that we got to, and now the Lagrange equation of motion is d to dt dl dx dot minus dl dx equals q. So dl dx dot, this is L, divided, then taking the derivative with respect to x dot, half of mx dot squared, so the derivative is mx dot. D to dt of this is mx double. Now we can take the derivative of L with respect to x. So there is no x here, but there is x in this second term. So the derivative of this is 2.5 is vanished, and we have x times k minus times x minus x0 with the minus here and here, and we get another minus here. So we get plus k. And then we have the external force, Q. Q is the force times dr dq. R is where the force is acting, which is x. So it's dx to dx, it's 1. So it's only x. So we get the equation of motion. And this, surprisingly, is the same as the Newton equation of motion. But that was a very simple example, just to show you that this is working. Now let's take a little more complicated example. And I think we'll finish with this example. Okay. So we have here a robot that can extend and can also rotate. So it has here a base that can rotate, and then the robot can extend, and it holds a mass at the end. So we have the inertia of the base. We have the displacement, how much it moves outside its d. It's another degree of freedom. We have theta, the rotation. Actually, this is the first configuration parameter. D is the second configuration parameter. And we have also mass at the end. And we have gravity. And we have external force X that push everything to the right. So let's see the kinetic energy. The kinetic energy of the firstly, the base that is only rotating, that it has only kinetic energy of rotation, which is omega transpose I omega, but omega is only theta dot. So we have I1 theta dot squared. And I1 is only VI around the ZX. Link 2. We have the kinetic energy. It's the linear kinetic energy plus the rotation kinetic energy. Again, because here it's only planar, the omega transpose I omega is simply I theta dot squared. So let's see what is I. I for a rod is simply for a very narrow rod of long one. So there is no I6 around this because it's very narrow. But around X, around Y and Z, we have 1/12 ml squared. This is around the center. So we get half of it. So it's 1/24 ml squared theta dot squared. This is actually this term. Now we need to discuss this term. This. So we take the location, the center of mass, this C. So if the entire length is 2L, this location is actually D minus L. This is D minus L. This is the distance from the origin to the center of mass. This is d minus L. Times cosine theta and sine theta. This is the center of location, the center of mass position. Then we take the derivative of this. So to take the derivative, we have only d and theta, which are parameters here. We change over time. So we take this with the derivative with respect to d. So it's d dot cosine theta minus this d minus L theta dot sine theta. This is the derivative of cosine. It's sine theta, theta dot. And since it's cosine, the derivative is minus. And the same for the derivative of sine. The derivative of sine is cosine theta dot. If I take v square, take the v times v, we get simply this d dot square plus d minus L square theta dot square. So this T2 is half of mv square. Mv square is n2 d dot square plus half n2 d minus L square theta square. And plus the rotation kinetic energy that we saw before. So this is the term. Now mass 3 also has some kinetic energy. The kinetic energy, since it's a point mass, it doesn't have a rotational kinetic energy. So it's only half m3 v3 square. And v3 square is similar to this, but we have only d, not a similar thing. So it's the same term here, but instead of d minus L, it's d squared. So the total kinetic energy is the sum of all the three kinetic energy of three masses, and this is what we get. Instead of the I2, it's actually the n square L square over 12, because we have the 2 here, the half here. So instead of writing this again, we just simply write I2. And this is the whole term of the kinetic energy. Now the potential energy. We have potential energy here due to gravity. So for gravity, the potential energy is mgh. So I take the mgh of the second and third mass, because they change the height. So the height of the center of mass of the second link is d minus L sine theta. This is d minus L sine theta is the height. So it's d minus L sine theta times n to g. And the same for mass 3, but instead of d minus L, it's only d. It's dn. And we also have an external force, F. F is horizontal, therefore its vector is F over 0, F and 0. And it acts at a point of the end effector, which is d cosine theta, d sine theta. Therefore, okay, I'll do this later. Therefore, we can develop now the equation of motion for Q1, which is theta. So we take dt to d theta dot. T is this term, and we take the derivative here, t. We take the derivative of t with respect to theta dot. So here there is no theta dot, only here. So it's only what's in here times theta dot. So you see, this is. And I need to take the derivative over time of this. So first I take everything times theta double dot. And then I take the derivative of what's inside. And what's inside, you see here, there's I1, I2, they are constant. But d is changing. So I have the square m2 d dot times d minus l, and you get here d dot d. And everything times theta dot. This is d over d, d to dt of dt to d theta dot. Now dt to d theta is 0. dv to d theta, I can go back. And this is v. And take the derivative of this with respect to theta. So we have sine theta here. So it will be minus cosine theta. Here, v dv, yeah, dv to d theta will be g cosine theta. And we have also the external force, F dot dr to d theta. R was d cosinus theta. So it will be minus d sine theta. So we have minus f d sine theta times f is f0. And yeah. What's here? And also we have the torque that the motor applies. So the motor generalized torque is tau, because it's tau d theta. So for the first equation of motion, we get all of these. This is the part of d over dt dl to d theta dot. This is all this. This is the part from the gravity, of the potential energy of the gravity. And this is the part of the external force. And tau is the part of the motor that is applied at theta. So we got all of this. This is the equation of motion. One of them, because we have 2 degrees of freedom, theta and d. So that was the first one. Now we can do the second one. So for d, dt to d dot is simply this. We take the derivative of this. It's this. Now we take dt to dd. So there's d also in the part of the theta dot. So we can take this. If you recall, this was t, and dt to dd is simply because of that we have d here, is taking the derivative of this. Yes. Then we need to take the derivative of v with respect to d, and this is it. Again, we take f dot drf to dd. We took the derivative with respect to d because it was d cosine theta and d sine theta. So it is f cosine without the d. And now we can assemble everything together and get the second equation of motion. This is actually the force. This is the external, the force that acts along the linear joint, yes, and F cosine theta is the external. We can assemble everything and get a second equation of motion. Any questions about this? No questions? So it kind of very simple system. You see this, only 2 degrees of freedom, but 3 masses. And we get very complicated equations of motion. This is the first equation of motion, and this is the second equation of motion. And this is actually how the system is moving. Now we can simulate this, we can integrate this numerically and see how it moves when we apply that force or other force and get all the dynamics of the system. But this is the essence of getting the dynamics of the system. For a robot, it's much more complicated because we have more links. The links are moving much more in a much complicated way. So the equations will be much bigger, much longer. But the idea is the same. Next week, we'll see what we can do with those equations of motion. Okay, so I think that's enough for today. It was a bit complicated. So we'll see you again next week. Bye.